So we're continuing with a few more examples of situations where we are going to need to find vertical and horizontal asymptotes of a function using limits. So let's remember, where does a vertical asymptote occur? Vertical asymptotes occur where this function is undefined. And we remember what makes a function undefined. So we've got a few different things. We can either have a 0 in the denominator, we could have a negative inside of a square root, or we could have a 0 or negative inside of a logarithmic function. These are generally the things we're going to see when a function is undefined. So I've got a square root in the denominator. Now, if 2x squared plus 1 is negative, that's going to make this undefined, or if 2x squared plus 1 is equal to 0, again, because the square root of 0 is 0, that would also make this undefined. So I want to set 2x squared plus 1 equal to 0. We agree that this would make this function undefined. Well, if I solve for x, I'm going to subtract 1 from both sides. I get 2x squared equals negative 1. Dividing by 2, I get that x squared is equal to negative 1/2. And now, if I solve for x, and I take the square root of both sides, when I have the square root of a negative, remember that that doesn't exist. That's an imaginary number which is not going to occur on our coordinate plane. And so in other words, there is no x value that's going to give us a denominator of 0. What if I were to replace this sign with a less than sign? What if I were to say that this is undefined when 2x squared plus 1 is less than or equal to 0? Less than or equal to 0. If this denominator is 0, or if we have a negative inside of a square root. Well, if I just change this equals to a less than, then I've got the same thing. Where is x squared less than or equal to 1/2? Well, when I solve for x and I take the square root of a negative, this is going to give me an imaginary number as well. So in other words, since there are no x values that will make this function undefined, there are no vertical asymptotes. There are no vertical asymptotes. So now for the horizontal asymptotes. Horizontal asymptotes occur when the limit as x approaches either positive or negative infinity, I'm just going to write that positive or negative infinity notation, of this function exist. This means when I take the limit as x approaches some form of infinity and I get a finite value, that is going to be our horizontal asymptote. So that's what we're going to do. We're going to take the limit as x approaches positive infinity of this function and as x approaches negative infinity of this function. So let's start with positive infinity. The limit as x approaches positive infinity of 3x minus 2 divided by the square root of 2x squared plus 1. Now, if I were to plug in infinity, or if I were to plug in an infinitely large value, my numerator is going to get larger and larger, and my denominator is going to get larger and larger. And so for that reason, I'm going to use that technique of dividing by the highest power of x in the denominator. Be careful here, because in my denominator, I have an x squared inside of a square root. And so what that means is that I'm going to divide everything by either the square root of x squared or just x, depending on if this division is occurring inside of a square root or outside of a square root. because the square root of x squared is just x, right? And so let's do this algebra. So I'm dividing 3x minus 2. Now since this isn't inside of a square root, I'm just going to divide that by x. And my denominator, since my 2x squared plus 1 is inside of a square root, and I want to perform this division inside of my square root, I get the square root of 2x squared plus 1 divided by x squared. Really doing the same thing in the numerator and in the denominator. So this is sound. We're not changing the value of this expression. Let's simplify this. 3x divided by x is just 3. Then we have a negative 2 divided by x. And inside of our square root, we have 2x squared divided by x squared. That's just a 2 plus 1 divided by x squared. And so now I'm taking the limit of this expression as x approaches infinity. The limit of 3 minus 2 over x divided by the square root of 2 plus 1 over x squared. And I know that whenever I have a constant in the numerator and a variable in the denominator and x in the denominator, as x approaches infinity, these fractions are going to approach 0. They're going to approach 0. So what's my limit going to be? In the numerator, I'm left with 3. And in the denominator, I'm left with the square root of 2. And I remember that horizontal asymptotes have some equations since they pass through the y-axis. They'll have the equation y equals whatever this limit is. So y equals 3 over root 2. This is one of our horizontal asymptotes. Now I also need to find the limit as x approaches negative infinity. The limit as x approaches negative infinity of the same expression. Now, if I do the same thing, if I divide by the highest power of x in the denominator, can I see that I'm going to get the same exact thing here? Because we said earlier in the previous video that even if I plug a negative infinity inside a denominator and I have a constant numerator, this term is still going to go to 0, just from a different direction. Let's look at a graph of this. Let's look at what we want to find. So let's graph the quantity 3x minus 2 divided by the square root of 2x squared plus 1. Let's go to a standard window. So I found that I have an asymptote at y equals, this was 3 over root 2, 3 over root 2. And I can actually plot this. Let me see what this looks like. That y equals an asymptote of positive 3 divided by root 2. And so graphing this, I get this line. This is my 3 over root 2. So I can see that this looks like where my asymptote occurs. What that means is that this curve, it gets closer to 3 over root 2, to y equals 3 over root 2, and never quite touches it. But I see something different down here. I see an asymptote that has y equals some negative value because it's below the x-axis. So what does plugging in this negative infinity do? Well, let's remember something important. The square root of x squared, the square root of x squared is not really equal to x. We oversimplified. Instead, the square root of x squared is equal to the absolute value of x. Now we already created a piecewise function for the absolute value of x. We said that the absolute value of x is equal to positive x if x is greater than or equal to 0. The absolute value of x equals negative x if x is less than 0. So we were correct by plugging in x when x approached a positive infinity, because when x is getting larger and larger in the positive direction, that means that x must be greater than or equal to 0. And so we are going to divide this, because x is approaching negative infinity, we are going to divide by the square root of x squared, or negative x, because x is approaching negative infinity. When we're approaching negative infinity, the square root of x squared is going to be equal to negative x. And so I'm going to do the same thing as I did above, except instead of dividing by x, I'm dividing by negative x. So 3x minus 2 is now going to be divided by negative x. And in my denominator, I'm still dividing by that square root of x squared down here. So this is still going to be the square root of 2x squared plus 1 divided by x squared. And I know when I simplify this, I'm going to take the limit. So let me just take the limit at this point. So I'm taking the limit as x approaches negative infinity, and I'll just simplify this expression inside of my limit. So now I have 3x divided by negative x. Now 3 divided by negative 1 is negative 3. And so now I have negative 3. Negative 2 divided by negative x is positive 2 over x. And I've got the same exact thing in the denominator as I did up here. I've got the square root of 2 plus 1 over x squared. All right, so now, as x is approaching negative infinity, all these terms with a constant in the numerator and some form of x in the denominator are going to go to 0 as x gets larger and larger in the negative direction. And so I am just left with negative 3 over the square root of 2, giving me my second horizontal asymptote of y equals negative 3 over root 2. And let's go back to our graph and make that lines up. So is our other asymptote negative 3 over root 2? Yes, it looks to be about right. Okay, so on to the next problem. We want to find all vertical and horizontal asymptotes for f of x equals 2e to the power of x divided by e to the power of x minus 5. Starting with vertical. For a vertical asymptote, I need to make this function undefined. Vertical asymptotes occur where this function is undefined. And I'm looking for things like a negative in a square root, a 0 in a denominator, or a negative or 0 inside of a logarithm. Now I don't have a square root or logarithm, but I do have a denominator, so let's see if there are any x values that will make this denominator equal to 0. Meaning, I can set this denominator, e to the power of x minus 5, equal to 0 and solve for x. So solving this equation for x, I'm going to start by adding 5 to both sides, and I get e to the power of x is equal to 5. Now here's the question, how do I isolate this x? Well, I know when I have an equation, what I do to isolate a variable is kind of the opposite operation. Since I have this e to the x minus 5, to isolate this e to the x, I just did the opposite of subtracting 5. I added 5. So the question is, what is the opposite of having e as a base and that variable being raised to that power? Well, I can do the opposite by taking the natural logarithm of both sides of the equation. When I take the natural logarithm of e to the power of x on the left side and the natural logarithm of 5 on the right side, doing the same thing to both sides, well, the natural logarithm of e to the power of x is just x. On the right, the natural log of 5 is just a constant, and I want to leave that as the natural log of 5. Unless I'm asked to approximate in the form of decimal, I always want my final answers in the form of the exact answer, so no decimal approximations. So this is my vertical asymptote. X equals the natural log of 5. And now for horizontal. For horizontal asymptotes, I need to find the limit as x approaches positive and negative infinity. So let me start with the limit as x approaches positive infinity of 2e to the x divided by e to the x minus 5. So as x approaches positive infinity, well, I can see that if I essentially plug in infinity, I can see that this numerator is going to get really, really big. This denominator is going to get really, really big. So this doesn't tell me much. And so I'm going to divide by the highest power in the denominator. Now, what is that? Well, we don't exactly have a polynomial in the numerator and the denominator, at least not in an ordinary sense. And so I'm going to divide by the thing that's making this denominator the biggest. So when I plug in infinity, e to the power of infinity is going to get really, really big, so I'm going to divide by e to the power of x. I'm going to do the same thing to the numerator and the denominator. So I am taking 2e to the x divided by e to the x, and that's going to be all over e to the power of x minus 5 divided by e to the x. So now all I have to do is simplify this expression, and I know I'm going to end up taking that limit. And so I'm taking the limit as x approaches infinity. 2e to the x divided by e to the x is just 2. And then in my denominator, e to the x divided by e to the x is 1. And then I can't simplify that minus 5 over e to the x. Now, e is a constant, and e is about 2.71. So what's going to happen as I raise a constant to a power that's really, really large? Well, as x increases, and let me write this as a side note, as x increases, e to the power of x is going to get really, really large. In other words, I can say that the limit as x approaches infinity of e to the power of x is equal to what? What happens to e to the power of x as x increases? Well, this value is going to continue to increase, so this is going to be infinity. Now, why is that important? Because this tells me that just like when I have a constant over some form of x as x approaches infinity, if I have a constant over something that's getting bigger and bigger, as my denominator is getting bigger, this term is going to go to 0. And so what am I left with? I'm just left with 2 over 1, which is equal to 2. If I have a limit as x approaches infinity of 2, that means I have a horizontal asymptote at y equals 2. Horizontal asymptote at y equals 2. What happens in the negative direction? So what happens as x approaches negative infinity of 2e to the x divided by e to the power of x minus 5? What happens in the negative direction? So what happens as x approaches negative infinity? Well, to figure out what really happens, let's look at e to the power of negative infinity. We've already said that the limit as x approaches positive infinity of e to the power of x, because some constant raised to a really large power is going to be really large. But what happens when we raise a constant to a really large negative power? So I want to know the limit as x approaches infinity, negative infinity, of e to the power of x. Well, let's do a little bit more work on the side. When I have some base that's a constant, let me call this a base e, and this is raised to a negative power, e to the power of negative a. This is equal to 1 over e to the power of a. I can make this a constant positive exponent by throwing this term in the denominator. And so the same idea applies here. E to the power of x as x approaches a really large negative number. Well, if I plug in negative infinity, if e to the power of x is approaching e to the power of negative infinity, well, this is really 1 over e to the power of infinity. And I know that when my numerator is a constant and my denominator is a really large number, this is going to get closer and closer to 0. In other words, the limit as x approaches negative infinity of e to the power of x is equal to 0. What if we didn't know that? What can we do about it? Well, if you're not convinced that the limit as x approaches positive infinity of e to the power of x is infinity, and as x approaches negative infinity, e to the power of x is 0, let's graph e to the power of x. We can absolutely graph whenever in doubt. Graphing e to the power of x, I know that as x gets larger and larger, y is going to get larger and larger. But I can see that as x gets to be a larger and larger negative, it almost have an asymptote right here. So let me adjust my table settings. I want to go to auto, just so this table will automatically populate. And now I can see that as x is getting smaller and smaller, can I see how my y values are getting closer and closer to 0? So that's going to confirm my limit. What does that mean? Well, that means that as x is approaching negative infinity, this limit is going to equal 2 times 0 divided by e to the power of x as x approaches negative infinity is 0 minus 5. What happens when I have a numerator of 0 and a denominator of a constant? Well, this is just going to be 0. If I have if I have a limit as x approaches negative infinity of 0, that means I have another horizontal asymptote at y equals 0. So I have a vertical asymptote at the natural log of 5 and 2 horizontal asymptotes at y equals 2 and y equals 0. Let's graph this. So I have 2 e to the x, just inserting some parentheses, 2 e to the x divided by e to the x minus 5. And I have a vertical asymptote at the natural log of 5. I have a vertical asymptote at the natural log of 5, which looks to be maybe between 1 and 2. Let's see, the natural log of 5. Great, that's 1.6. That's about what it looks like. I have a vertical asymptote at about 1.6, and then I have 2 horizontal asymptotes at y equals 2, and then another one at y equals 0. So we found all vertical and horizontal asymptotes. All right. Example 8, and we just switched example 8, so we're only really worried about the horizontal asymptotes. We want to find the limit as x approaches infinity of x plus the square root of x squared plus 2x, and the limit as x approaches negative infinity of that same function. So we want to find those limits as x approaches positive and negative infinity. So first, let's just take a look at what happens when I plug in an infinitely large value. When x approaches positive infinity, if I just plug in infinity, then I'm going to get infinity plus the square root of, well, infinity squared is just some infinite value, plus 2 times infinity, well, that's another positive infinite value. If I'm replacing these infinities in my head with just really large positive numbers, can I see that as x gets larger and larger, this entire expression is going to get larger and larger? And so I can say that the limit as x approaches infinity without doing any other work of x plus the square root of x squared plus 2x is just going to give me infinity. In other words, when x approaches infinity, the limit does not exist. This is our final answer. So we can look at these logically, because remember that that's kind of what we're doing. I'm just seeing what happens to this function as x gets larger and larger. Now let's look at the limit as x approaches negative infinity. Well, when I plug in a really big negative number, I'm going to get negative infinity plus the square root of, well, when I square a negative value, this is going to become a positive. And then I'm adding 2 times negative infinity. Okay, that's going to be a negative value. What is this going to look like? Well, I really don't know. I know that if I'm just adding a whole bunch of infinitely large values, this is going to continue to increase. But if I'm subtracting some of them, I don't know which one's going to kind of outrun the other as x gets really, really large in the negative direction. So I don't know what this is. And so I need to do a little bit of algebra with this problem. And so what I'm going to do is, I see a square root in this case. I'm going to multiply by the conjugate of this term. So I'm going to multiply x plus the square root of x squared plus 2x. I want to multiply this by the conjugate, which means I'm just flipping this middle sign, and let me put parentheses around the two terms. I'm just flipping this plus sign to a minus and leaving everything else the same. This looks a lot like my process of rationalizing when I wanted to get rid of the discontinuity. It's just another technique that I can use to put this in a form that I can find the limit of. Now, if I multiply something by an expression, I need to divide by it as well. So I'm kind of multiplying by a fancy form of 1 so that I don't change the value of this function. Now, what is this going to give me? Well, I know that when I multiplied by a conjugate, what I'm really doing is I've got two binomials and I'm really foiling them. Because I'm multiplying by the conjugate, my inside and outside terms are going to cancel. And so I'm just left with the first terms squared, so x squared, plus the outside or the last term squared. So the square root of x squared plus 2x times negative square root of x squared plus 2x. When I multiply an expression inside a square root by itself, that square root's just going to cancel. And so I'm going to have minus x squared plus 2x, making sure that I have parentheses around this expression because I'm subtracting this entire expression. And I'm just dividing this by what I have in this denominator, x minus the square root of x squared plus 2x. Let's see what happened. Well, now I've got x squared minus x squared minus 2x. My x squareds are going to cancel out. So this is going to give me negative 2x divided by x minus the square root of x squared plus 2x. Let's think about what would happen when I throw a really large negative number inside of this expression. Well, my numerator is going to be negative 2 times negative infinity. All right, that's a positive, infinitely large number. And then in my denominator, I'm kind of left with the same thing. I've got a negative infinity. I've got, because this is squared, a positive infinity in this denominator. So I still have some type of infinity over infinity. Now I'm going to use that technique of dividing everything by the largest power in the denominator. I'm going to divide by the square root of x squared, or because I'm going to negative infinity, the square root of x squared, because it's really the absolute value of x, it's going to be a negative x, because x is approaching that negative infinity. So let's do that. So this is going to be negative 2x divided by negative x divided by x divided by negative x minus the square root of x squared plus 2x divided by x squared. We made that an x squared inside of our square root. Finally, we are taking that limit. So we're taking the limit as x approaches negative infinity, and I just want to simplify this as much as possible. Negative 2x divided by negative x is a positive 2. X divided by negative x is negative 1, and I'm subtracting from it the square root of x squared divided by x squared, which is 1, plus 2x divided by x squared. Well, that's going to be a 2 over x. I know when x gets really, really large, even if it's in the negative direction, this 2 over x is going to approach 0. And so what am I left with? I'm left with 2 divided by negative 1 minus the square root of 1. The square root of 1 is just 1, and negative 1 minus 1 is negative 2. And so this is going to give me 2 over negative 2, or just negative 1. And so my limit as x approaches negative infinity of this expression is negative 1. And so if I were to graph this, I would see a horizontal asymptote at negative 1. So go ahead and graph this just to confirm that you see that horizontal asymptote at negative 1. All right, one more problem. Now we've got the limit as x approaches infinity of 2x to the 4th power minus x squared minus 8x, and we've got the same deal as x approaches negative infinity. So first, as x approaches positive infinity, what's this going to give me? Well, plugging in infinity, I get 2 times infinity to the 4th power. All right, that's a positive infinite value, minus infinity squared, so minus infinity, minus 8 times a positive value, that's another minus infinity. Infinity minus infinity minus infinity. Well, I don't exactly know what this is. If I take a really big number and subtract from it 2 other really big numbers, I don't know which number is biggest. And so this is the technique I'm going to use. I'm going to take that limit as x approaches infinity, and I'm going to factor out the largest power of x. I am going to factor out, let me make note of this. I'm going to factor out the largest power of x. Instead of dividing by the largest power of x, when I don't have a quotient, when I just have a polynomial, I'm going to factor out the largest power of x. The largest power of x is x to the 4th power. So I'm going to factor out x to the 4th power. When I factor out a value, what I'm really doing is I'm really dividing all of these terms by that value. So when I factor out an x to the power of 4 from 2x to the power of 4, I'm just left with 2. When I factor x to the power of 4 out of x to the power of 2, I'm left with negative. X squared divided by x to the power of 4 is 1 over x squared. And finally, negative 8x divided by x to the power of 4 is negative 8 over x cubed. Now what happens as x approaches infinity? And remember that when I factor something, I'm not changing the value of it. So this is a perfectly sound operation. As x approaches infinity, both of these terms with a constant in the numerator and x to the power of something in the denominator are going to get closer and closer to 0 as x gets larger and larger. And so what am I left with? I'm left with the limit as x approaches infinity of 2x to the 4th. What happens as x gets larger and larger? Well, this term also gets larger and larger. And so this is going to go to infinity, where we can say that that finite limit does not exist. All right, one more. Let's look at what happens as x approaches negative infinity. So just thinking, if I plug in a negative infinity, I have 2 times negative infinity to the 4th power. Well, this term is going to be positive because when I raise a negative to an even power, it's going to give me a positive. Minus negative infinity squared, okay, that's just going to be minus infinity. And then minus 8 times negative infinity is going to be plus infinity. Still don't know what that is. I don't know what this is. And so let me use the same kind of idea here, and I am going to take the limit as x approaches negative infinity, and again, I'm going to factor out an x to the fourth power, and I'm going to get the same exact factored form. So I'm going to get x to the fourth power times 2 minus 1 over x squared minus 8 over x cubed. And again, as x approaches negative infinity, any constant in the numerator and variable in the denominator is going to go to 0. And what am I left with? Again, I am just left with the limit as x approaches negative infinity of 2x to the fourth power. And again, when I plug in a negative, negative raised to an even power is going to be positive, so this is going to be some sort of infinitely large positive value. Therefore, that finite limit does not exist. All right, and that is our last example of finding limits at infinity.